I got all my A students here. The ones that show up early. This is here. Shirley's here. Victor's here. That's good. That's good. Doing good. Okay, let's go ahead and finish up. Last day of notes for new material. That's it. Exciting times. Okay. Okay. Applications of Taylor polynomials. Okay, applications of Taylor polynomials. Okay, number one, we want to approximate the function, okay, f of x is equal to the cube root of x by a Taylor polynomial of degree 2 at a equals 8. Taylor polynomial of degree 2 at a equals 8. Okay. So, okay. And find, okay, then find the accuracy of this approximation for 7 to 9, between 7 and 9. So what's our radius of convergence? Our radius of convergence here is going to be 1. Okay. Think of it as how did we get this? We did x minus 8 is less than or equal to 1, right? So think of it like that, right? Because that's going to be our kind of like our radius of convergence. Okay. Okay, we want to find the accuracy for radius of convergence of 1. Okay, so first let's find the Taylor polynomial itself for the cube root of x. Okay, so I'm going to rewrite this as f of x equals x to the 1/3. Okay, what does this thing look like? Well, looks like this. Okay. Actually doesn't look like that. Looks, that's inverse tangent. This guy looks more like this. It goes flat. It goes all vertical for 1 point, 1 instance, and then it goes like this. Okay, so there's no asymptote though. It just continues to go up. And this has no asymptote either. Let's just, let me see what I can do with this thing. This thing goes like so. Nope, that's not what I wanted. White pen is what I want. Is there a white pen? Give me a white pen. Come on, come on, come on, come on. Come on, come on, come on. Come on. Oh, here we go. This could be, nope. Come on, go back. Go back. Just give me a white one. Give me the white pen. There we go. Okay, let's see. Yay, now I can erase. Erase, 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 erase. It's too steep on the incline there. So now let's go back to red. Let's see if we can make this a little bit nicer. Okay. What that would you no, what happened there? Give me the white one back. Say goodbye to this guy. There we go. Stop. Be nice. There. Okay, so there you get an idea of, oh, geez. Okay, there you get an idea of x to 1/3, right? And we want to know what's happening at this thing at 8 when x is equal to 8. So I'm gonna do like a 7 to 8 type of thing here. Okay, so around 8, what's happening? So I'm just gonna pretend that this is 7, this is 8, and this is 9. Okay. Hopefully you're okay with that. Okay, so we want to know what's happening at 8. We want a function that really is a good approximation, but we want a quadratic that's a good approximation at x equals 8. So let's do the Taylor polynomial for this. Okay, so f of x is equal to, okay, f of, what do I want here? F of 8. Okay, I'll just put f of a here for the moment. Okay, plus f prime of a times x minus a plus f double prime of a times x minus a squared. Okay. Okay, so I just want to find out what these things are. Okay, so let's do f of 8. What's f of 8? Well, that's 8 to the 1/3 power. 2. Okay. What's f prime of x? Okay, f prime of x here is going to be 1/3 x to the negative 2/3, right? So this is going to be equal to 1/3 x to the 2/3. So f prime of 8 is going to be 1/3 times 8 to the 2/3. So that's 4/12. I think this is 1/12. That's 1/12. Okay. Okay, this is going to give me my coefficients, basically. Okay, and so then what's f double prime of x? Well, this is going to be negative 2/9 x to the negative, I want to go down 3 more, negative 5/3, I believe. Okay, evaluate this guy. This is 1 over, or this is negative 2. Negative 2 over 9 x to the 5/3. Okay, evaluate this at 8. F double prime of 8. Okay, is equal to 1 over, or sorry, negative 2 over 9 times 8 to the 5/3. Well, 8 to the 1/3 is 2. 2 to the 5th is 32. So that's going to cancel with the 2 on the top. So this is negative 2 over 9, 32. So that's going to be, boom. Okay, that's going to get me negative 9 times 16, which is 144. 9 times 16 is 144. So those are coefficients. Okay. So let's see what we got here. Okay. Oh, you know what I forgot? I forgot the 2 factorial here. My bad. Okay. 2 factorial, yeah. Okay, so f of x is equal to f of 8 plus f prime of 8 times x minus 8 plus f double prime of 8 times, or over 2 factorial. I keep forgetting the 2 factorial. F double prime of 8 over 2 factorial times x minus 8 squared. Okay. And so this is going to be 2 plus 1/12 times x minus 8 plus f double prime of x is negative 144, but I need to divide that by 2 factorial, which is just 2. So this is going to be minus 1 over 288 times x minus 8 squared. Okay, so that's a parabola. I'm not going to simplify that, okay? But so f of x is approximately this at x equals 8. It's approximately this out to, okay, and I want to know about how accurate is this between 7 and 9. Okay, so again, let's go to the calculator real quick, because the picture is worth 1,000 words, right? So let me do my share my screen. Share. Okay, so here's my function, and I want to go to my calculator. Okay. No. No. Next. Okay. And oh, do we want to do that on the calculator? Desmos. Let's do, well, let's do Desmos. I mean, it really doesn't matter. We could do it on the calculator. Let's try it on the calculator. Okay, like I said, it really doesn't matter. Desmos, it might be a little nicer. Okay, but all I want to do is graph these two functions. That's it. That's all I want to do. Okay. So let's see. Let's just go to the graphing. Okay, y equals. I'm going to go clear, and I'm going to go the cube root of x. So I'm going to go x to the 1/3. Okay, so x raised to the 1/3. Does that work? Maybe? No? To the parenthesis, 1 divided by 3. Okay, enter that guy. And then clear. Okay, this guy out. And I want my new polynomial, which is going to be 2 plus 1/12 times x minus 8. X minus 8. Okay, minus 1 over 288 times x minus 8 squared minus 8 quantity squared. Okay, so we get this. Stop, 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 go back. Go back. There we go. Okay, so let's graph this and see. I'm going to alter my graph. The blue line is going to be cube root. The red line is going to be, okay, so I am going to alter this a little bit. This is a parabola. Okay. Ooh, just hugs that line there. That's a parabola that just hugs that line. Okay, and so I'm going to zoom in a little bit on this one. I'm going to say that I want my window. I still want to go from I don't need my x's to go that far. I'm going to go 0. Okay, for my x's. My y's, I don't need to go as far as well. I can do my y's from, say, negative, I don't know. What do I want? Like -3 to 3? Yeah, let's do that. -3, I don't even need to go to -3, but I'm going to go -3 to 3. And I'm going to graph this thing again, see what we get here. Okay, so that's That's x cubed, or x to 1/3. Okay, that's that blue line. Okay, and then the red one is the, just hugs that thing. That's so cool. And, you know, where's 8? Well, 8, it would go 8. 8 would be about, I'll show you. I'll just trace it. Trace. Where's the trace? Trace. Okay, well, then we'll trace it on the blue one. Yeah, let's go x is equal to 8. Okay, you can see that at 8 it's 2, and it really does. I mean, it's a very good approximation. Okay, and we want to see, okay, what is the accuracy of this approximation around 8? If I look at 7, it's still really close. I mean, it's really hard to tell any difference between the two graphs at 7, or what about 9? Again, it's really close. Let's see what happens. Let's look at the error. I'm gonna have to write this down on a piece of paper because I don't want to have to keep switching back and forth. But if I'm on the actual function at, let's do 7 again. We'll go back to 7. If I'm on the actual function, f of x equals x to the 1/3, that's the blue line here, right? So when x is 7, right, y is equal to 1.9129312, okay? And when x is 9, what am I at? When x is 9, I'm at 2.0800838. Okay, when I'm at 9, right? Okay, that's cool. Okay, what about when we go to the red line? So I'm just going to arrow up, and now I'm on the red line. Okay, so I'm going to go when x is 7 on the red line. Okay, and this is our approximation, right? Our approximation. We would get y equals 1.913, so pretty close. 31944. Okay, 1944 there. Okay, that's for our parabola when x is equal to 7. Okay, before we got a 0.1929, here we're getting a 0.131, pretty close. Okay, we're within about I want to say 2/1000ths. No, not even that. 2 10,000ths. We're within 2/10,000ths. Okay, between those. And then let's do x equals 9. Okay, when x is equal to 9, well, yeah, this is 2.0798. We got 2.08 basically last time. Okay, not much of an error. Okay, there is an error, and we're going to talk about what the error is. 798611. Okay, so let's go back to our notes here, and I'm gonna talk about this. What happened when for the original function f of x equals x to the 1/3, or we'll just do cube root of x. Cube root of x. When x was equal to 7, okay, we got y equals 1.912 9129312. Okay, and then but when f of x was equal to our approximation, which is, I'm just going to say C above, okay, this thing here, okay, then f of x is approximately, okay, x equals 7, then y was equal to 1.1944. There's a 9 there. 1944. Okay, so you can see how close it is. Wait, 191. There's a 1 there as well. 1319. So this basically was a 29. And this is basically like a 3-2. Okay, so again, the first 3 digits, very accurate. Okay, very accurate. Okay, so what about when x was equal to 9? When x was equal to 9 for the cube root of x, y is equal to 2.00, nope, 2.0, 800, 838. 838, okay. Nice, 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 nice. And then when x is equal to 9 for the approximation, okay, see above, okay. Okay, then y was equal to, what? Y was equal to 2.079, okay, 2.079, 869, 2.079, 8611. Okay, so now with modern computers, we can calculate these errors here. The error, right? What would be the error between these two? Okay, I could do that pretty easily. Okay, let's just go back to the calculator. Okay, actually, I'm going to do it on my handheld because I can't be flipping back and forth between these two. Okay, so at x equals 7, the error is equal to what? I'm going to take the bigger one minus the smaller one here. I could just do the absolute value, but it really doesn't matter. We're just going to do absolute value of the error. Okay. Okay. Okay, when x is equal to 7, so I'm going to take these two, I'm going to subtract them. We'll go 1.19131944 minus, let me make sure I did that correct, 1.19131944, that's correct, minus 1.19129312. Okay, and I'm getting 0.0000, okay, 2632. Okay, that's the error for when, okay, well, that's the error for when x is equal to 7. Okay, so what's the error when x equals 9? Because we want to go with kind of the bigger error. We want to say, hey, you know, which one's bigger here? Okay, so the error in this case, okay, when x is equal to 9, let's subtract these two. That's going to be 2.0800838 minus 2.0798611. Enter, and I'm getting, did I do that right? Wait, let me check my work here. I think I did miss something. Okay, so 2.0800838 minus 2.0798611. Okay, I think that's good now. Okay, and I'm getting 0.00227. Okay. So one less zero here. So these are not the same decimal place accuracy. Make sure I did that correctly. Yeah. Did I? Search. Okay, so you subtracted from the original by the approximate. Or does it not matter? No, that's what I'm doing. I subtracted the approximate value from the original value at x equal, I evaluated these at x equals 9 and x equals 7. And then I'm subtracting, this is, the approximate one is the quadratic, right? Okay, so I'm saying how far did the quadratic veer from the original function? How far is the Taylor polynomial away from the original function at x equals 7 and x equals 9? It's at x equals 8, it's exact. It's exact. Okay, at x equals 8, y equals 2. Okay, that's a done deal. You know that. Okay, because we built the Taylor polynomial to be that. Yeah. So use the original to find the approximate minus the approximate to find the error. Yeah, with the absolute value bars. Victor, does that make sense? So yeah, so that's what I'm doing here. I'm subtracting these two with the absolute value bars. Maybe I should have stated that. Okay, so the error is going to be the difference between the two. So, you know, cube root of x. I don't know how to rewrite this, but it's the x to the 1/3 minus the x squared polynomial absolute value, right? So absolute value x to the 1/3 minus the x squared polynomial, blah, 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 blah. Okay, so yes, it's just the remainder. It's the error. So yeah. So yeah, I guess I could have been more specific, but this is 0.02270. Okay. So which one gives me the bigger error here? Well, x equals 9 gives me the bigger error. Does that make sense? Okay, so what I might want to do is say this. Okay, let's say this. Let's say that just to be safe, we would take the bigger error and we would say, well, the error, you know, on 7 is less than or equal to x, which is less than or equal to 9. The error bounded, the error would be bounded by, we'll say, I'm going to maybe even round this up to the next digit. You know, I don't know. I don't know how you want to do this, but you know, I need to be above this thing. I need something that's I need something that's greater than this. Does that make sense? I want it to be a boundary on this thing. I don't want to be lower. If I round this thing, I'm going to get a number lower. Does that make sense? So I want a number. So maybe I would say that it would be bounded by 0.000, okay, 23. Does that make sense? Okay, or maybe I could even go to something that would round accurately and maybe go 223. I just need to make sure that it's bigger, that this guy is bigger, right? Because it's an upper bound. It's an upper bound on my error. Does that make sense? Now, we did have, okay, so the error is within this. It's within this. It's to 1, 2, 3 decimal place accuracy here. Okay, does that make sense? Okay, so we do have a formula that we can use to get an approximate error. See, before we had computers, okay, we would have to do this more by hand. Okay, and so here's what we would say. We would say, well, what's the remainder of a second degree Taylor polynomial? What's the remainder of a second degree Taylor polynomial? And this would be less than or equal to m over, okay, n plus 1 factorial. Maybe I should put in the function that we talked about yesterday. Okay, n plus 1 factorial times the absolute value of x minus a to the n plus 1 term. We're looking at the next term, okay, in this thing, and we're right. where m, okay, is greater than the nth derivative, okay, is it the nth derivative or the n plus 1th derivative? I think it's the n plus 1th derivative, yeah, to the n plus 1th derivative of x, okay? I believe that was what we talked about briefly yesterday. Yes, it is, okay? For x minus a is less than or equal to d, okay? For x minus a is less than or equal to d. Okay, cool. Okay. Yep. There we go. Okay, so what we want to do is we want to plug in the numbers now. So we want to say R2 of x here, the remainder for this thing, the second, right, is less than or equal to m, okay, right, so this thing is less than or equal to m, right, so basically what this is saying is this, okay, so let's put this guy in real quick. So f to the n plus 1th derivative of x all over n plus 1 factorial x minus 8 in this case, right? Because a is 8. Okay. And then the n plus 1 is going to be 3. So let's do the third derivative. So 1, 2, 3, third derivative of x over n plus 1. That's just 3 factorial. Okay, that's 3 factorial. Okay. And then this is to the third power. It's actually absolute value. Okay. Okay, to the third power. Okay, which is less than or equal to m over n plus 1 factorial. Okay, and then x minus a to the n plus 1, right? So this is, again, 3 and 3. So I'll plug in the numbers for our specific. This is what it means. Okay, if I can find an m that is just slightly bigger than my third derivative evaluated at 8. Okay. Oh, this is it f sub x? Yeah. F sub x is blah 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 x minus x. Okay. Yeah. Yeah. So f sub x, we can find something that's slightly lower than that. Okay. Then yeah. And so this is going to be for, okay, x minus 8 is less than or equal to 1. Okay, why less than or equal to 1? Because it's bounded, okay, x is bounded by 7 and 9, right? So x minus 8 is negative 1 and 1. If I add 8, I get 7 to 9. Okay, so that checks. That works out. Okay, so what I want to do here is find, well, what's the third derivative of this thing? Okay, evaluated. Well, we'll get to that. We'll get to what it's evaluated at. Okay, so let's just find the third derivative. Okay, so f of x is equal to x to the 1/3. Okay. Okay, f prime of x is equal to, well, 1/3 x to the negative 2/3. F double prime of x, okay, f double prime of x is equal to, we did this before, negative 2/9 x to the negative 5/3, and f triple prime of x, okay, is going to be, what is this, 10/27 x to the 8/3, I want to say. Yeah, negative 8/3. Okay. So, yeah. Okay, and then we're gonna take, oh, I forgot to put the absolute value here. There's an absolute value here, there, okay. So let's look at the absolute value of this thing less than, this is a strict, sorry, that's a strict inequality. Less than some m, like, because we want to like say, okay, well, what's the boundary here for this thing, right? Okay, so, okay. So what we're going to do here is we're going to say that x, this is 10 over 27, absolute value 10 over 27, x to the 8/3, okay, is less than some m, right? Okay. Okay. So let's go back to this guy here real quick. And I'm gonna go 7 is less than or equal to x, which is less than or equal to 9, right? Okay. Okay, so so the idea is that let's raise each of these to the 8/3 power. 8/3, 8/3, 8/3, right? Okay, because I really want to find out what does m need to be here, okay, within this interval. Okay, and now what I'm going to do is I'm going to do the reciprocal of this thing. 1 over 7 to the 8/3, 1 over x to the 8/3, and then 1 over 9 to the 8/3. Now, when I do the reciprocal, what happens to the inequalities? Any ideas? What happens to the inequalities when I do the reciprocal of each of these? Is 1/2 bigger or smaller than 1/3? Okay, yeah, they reverse. Thank you, Victor. Okay, yeah, so think of it like 2 is less than or equal to 3, but 1/2 is bigger than 1/3. Does that make sense? Okay, so they reverse. So this is going to be like this, right? Okay. Okay, so now, okay, now we're going to multiply everything by 10 over 27. 10 over 27, 10 over 27, 10 over 27. Okay, so and which one's the bigger one now? Which one's bigger? Which one's bigger? Which one's the biggest one? Isn't this the larger of the two numbers? Right? Isn't this thing bounded by this number now? Above? Yeah, absolutely. So that's what m is. I'm going to say m is equal to the larger number, okay, because the inequality's flipped, and this is 10 over 27 times 7 to the 8/3 power. That's what m is going to be our bounded. It's going to be bounded by this thing. Okay. Okay. So that's our m. Okay. So we're going to say okay, we have okay, so the absolute value of r sub 2 of x, okay, is less than, okay, is less than or equal to is less than or equal to m over 3 factorial oh yeah, exactly, m over 3 factorial. So m over 3 factorial times the absolute value of x minus 8 raised to the third power over x minus 8 raised to the third power. Okay, so what's 3 factorial though? That's 1/6, right? So this is going to be it's going to be 1/6 times 10 over 27, 7 to the 8 thirds, times x minus 8 to the third power. Okay. Okay, let's, we're getting closer here to an answer that we can look at. Okay, so let's so we have 1/6 times 10 over 27, 7 to the 8th power. Okay, and what do I want? Okay, well, let's think about this for a second. Okay, so, well, let's clean this up real quick. Okay, this is going to be 5. This is going to be 3. This is going to be 5 over 3 times 27 is 81, I believe, right? Yeah, 81 times. So, come on. 81 times 7. Okay, 81 times 7 to the 8 thirds. Okay, times x minus 8 to the third power, right? So, okay. So the only last thing that we have to worry about now is, well, for what value do we want to bound this by, right? For what value do we want to bound this by? Well, what did we say? We said that the absolute value of x minus 8 is less than 1, less than or equal to 1, right? Does that make sense? Right? So this thing is less than or equal to 1 cubed. If I were to cube both sides, that thing would be less than or equal to 1 cubed, which is 1. Okay, that's our radius of convergence. Our radius of convergence is 1 here. So we want to bound this by 1. So this whole thing just goes to 1. Oh, well, that's kind of cool. So r sub 2 of x is really less than or equal to 5 over 81 times 7 to the 8 thirds power. Oh, okay. Because this thing just went to 1. Okay, so that would be the error on this thing. When x is between 7 and 9, the error would be, okay, bounded by this value. Okay, so let's figure out, well, what is that value? That value is going to be 5 clear. Where's my clear? Okay, 5 divided by 81, okay, times 1 divided by 7 to the 8 thirds power, parentheses, 8 thirds power, close parentheses. Okay, and I'm getting 0.0003443, 3, I'll say. Okay, I'll go all the way out until I can round up. Okay, so 0.00004. Sorry, I'll just 3.4. Okay, so let me write this down so I don't have to keep going back and forth. It's 0.0003443. Okay, 0.0003443. Okay, so let's say that's what this is, right? This is 0.0003443. That's what this is bounded by. Those are fours, by the way. Okay, that's what this is bounded by. So in the olden days, before computers, this is how they would have to calculate the error on these things. And what would they do? They would actually have a table of books that have these values, 7, 8 over 3, 7 to the 8/3. They would actually have computed these values, and then you'd have to go look it up in an anthology of, a table of values to get that value, and then you'd have to do some multiplication and division, and then you would come out with this value here, and they'd be like, oh, okay, so that's the error. That's how they'd have to do it pre-computer. We, living post-computer in the modern era, the information age, we can actually get a better approximation than they could back then. This is the pre-computer approximation, okay? Right? That's the pre-computer approximation. What did we got? We got an even better approximation. Okay, computer-aided approximation. We got 0.00, what was it? 0.244, no, 227, something like that. I forget. Let's go back up here. What was our computer-aided one? The error was 0.00223, right? So yeah, 223. Okay, so we got a smaller error bound. Theirs is fine. I mean, it's still within like 1/10,000th. Okay, 223, right? So computer-aided error is this one. Okay, but we got one. If we wanted to do it the old-fashioned way, this is how we would do it. Not computer-aided. Okay. Okay, let's do one last one of these. Okay, let's go backwards. Let's say that we want it within a certain degree accuracy. How many terms would we have to go out? Okay, so number 2 here. Okay, what is the maximum error? Oh, no, it tells me how many terms I'm going to go out. So we're just going to get maximum error. Yeah. Okay, what is the maximum error for sin x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, when negative 0.3 is less than or equal to x, which is less than or equal to 0.3. Okay, so we're gonna hover around that, which means that the value that we're gonna be looking at is 0, right? Which makes sense because this is a Maclaurin series, which means that the value that we're looking around is 0 when x is equal to 0. Okay, that's the value that we're looking around. Okay, and so sorry. Okay, so what's the maximum error on this thing, right? So let's write out the terms here, okay? The terms here, because I really want to know, like, well, how many derivatives am I going to have to take, right? And how many, like what's actually going on here? So I'm going to write it out like this. Sine of x is equal to 0 plus x plus 0 over 2 factorial x squared minus 1/3, 1 over 3 factorial x cubed plus 0 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th. Okay, let's do 2 more here. Okay, plus 0 over 6 factorial x to the 6th minus 1 over 7 factorial x to the 7th. Okay. Okay, so, okay, what is the maximum error? Okay, for this, when we're between 0.3 and negative 0.3. Okay, so we went out, okay, because really what this goes back to, the reason I wrote it out like this is because it goes back to the idea that we're taking the next term. We're taking the next term, which means that I had to go to the next term. Okay, after, I could have written it like this, okay, but it just helps me see, you know, this is actually the 8th term in this sequence or in this series, and so that's gonna, you know, that's gonna help. So I'll show you, this is x to the, right, the next term here is going to be a negative x to the 7 over 7, right? So that's the next term, okay, that we found here. Okay, that's the next term. Okay, so why is that so important? Well, again, let's look at the error, the remainder on r sub n of x. Okay, r sub n of x is less than or equal to, okay, m over n plus 1 factorial, right? So less than, it should be a hard less than, but whatever. Okay, less than m over n plus 1 factorial, okay, absolute value of x minus a to the n plus 1 degree, right? So n plus 1 degree, okay. So here, let's plug in what we know, okay, and we'll calculate m in a minute. And again, I'll show why we had to go out to 2 more terms instead of the next one. This is, why do we skip this guy? Okay, why is it important to go out to this one and find out, well, what's the index of that and everything else? So because this r sub n sub x, okay, what would be the next term? What would be the n plus 1 term, okay, that I would want to work with? The next term here would be this guy here. Okay, that would be the next term that I would want to work with, right? That's the next one. That's the, we'll say that's the n plus 1 term, right? That's the n plus 1 term. The whole idea is here, we want to find out what the heck is n. That's the whole idea. What is n if 7 is the n plus 1 term? Or wouldn't it be 6? Right, wouldn't it be 6? We would use 6 in this case as n, because this would be, right, what's the factorial here? The factorial is 7 factorial on the bottom, so n plus 1 equals 7, so n would have to be 6. Does that make sense? Okay. Okay. And we don't want to use 5. Okay, we don't want to use 5 because the derivative of the next term is 0. And 0 is not going to tell us much. Okay, we don't want to, we skip this one we skip this guy here, okay, because the m is 0, and to have the m be 0, that's not very helpful. So we skip that one and go to the next one, but that means our index goes up by 1. Does that make sense? Our n plus 1 ends up being 7 instead of 6. Because the next term here, it would be a 0. And we don't want the 0. We want the number here. We want the number here. Okay, which is -1 really. This is plus a -1, right? Okay, we'll get to that in a second. So what is the absolute value of f to the 7th degree of x, right? Okay, evaluated at 0. Okay, we'll just say what I want to here. Okay, yeah, we'll just say that. Okay, so f of 7, the 7th degree, okay, of x is what? Well, isn't f of x the sine function? Isn't f of x the sine function? So what is the sine function bounded by? What's the upper bound for the sine function? What's the upper bound for the sine function? Any ideas? What's the upper bound for the sine function? The upper bound for the sine function is what? Is 1. Very good. Thank you, Jean and Susan. It's 1. So doesn't this thing, regardless of what x is, if I keep taking, it's also cosines, right? Because what's the 7th derivative? Doesn't that just flip between sines and cosines, right? F of x equals cosines. And then if I do absolute value on this thing, right, the nth derivative of this thing, won't it always be bounded by 1? Right? Wouldn't that always be bounded by 1? Right? So you can kind of logic yourself through that. Does that make sense? Like, because all you're ever going to get when we take derivatives of this thing are going to be sines and cosines. Right? And if we take the absolute value of those, well, then that's going to be bounded above by 1. So the biggest number that you could ever have here for the 7th derivative here is 1. Well, we already know what the 7th derivative evaluated at 0 is. That's -1. The absolute value of that is 1. So we're going to let m equal 1. So let m equal 1. Oh, okay. So now let's plug in what we know. Let's do the absolute value. The absolute value of Rn. What's n in this case? It's 6. Okay, it's not 4. It is not 4. Why do I say that it's not, or not 3? It is not 3. It is not, n is not 3. Why is it not 3? Okay, why is it not 3? Because if you look at the original function for sine, the original polynomial, we're missing terms. If we go x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, right? You would think that, oh, well, there's just 3 terms here, but that's really not the case. What's really the case here is that there are 6 terms here. Okay, and we want and then there's a 7th term and then an 8th term. Okay, but we're shifting indexes. Okay, so n is not 3 for this r sub n. N is actually 6. It's twice as much because we had twice as many terms because we had those 0 terms. We included those 4 0 terms. Okay, so make sure you have your index, you're understanding your index here. Okay, so r sub 6 of x is less than 1 over, okay, is less than 1 over Okay, 7 factorial times x minus a, in this case, a is 0, to the 7th power, right? To the 7th power. Okay. Okay, so we know that this is, okay, r sub 6 of x is less than x to the 7th over 7 factorial. Okay. Okay, but what do we know about, and I'll put an absolute value here, if I can, if the computer will let me. Let me, absolute value. Testing, 1, 2. Did I freeze? It froze. Oop. Froze. Froze. Sucks. That it froze. Hola, ¿cómo estás? Muy bien. Gracias. ¿Y ustedes? The whole computer froze.